Hey, I found it. It fell out of the backpack onto the pavement. So, anyways, happens. Gotta make sure it's more secure next time. I found it. It just fallen out of the backpack next to the car. So I have it. I think I went over some content today at the end of last class. I have to review that because it didn't record. Jeez. Anyways, I'll go over. So I went over this just so it's recorded. I'll go over it a little bit more quickly here. This I did at the end of the afternoon class here. So I asked the question, what's the difference between one-dimensional and two-dimensional momentum problems? And I had you define that. Some of you already gone through this, so I'll give you the answer a little bit more quickly this time. But just so you know, I noticed some of you are still having problems with momentum, 2D momentum problems. So I think what I'm going to do is give you a little time to go over them yourself on that handout, and then go over some of those questions on the handout for you. I have to do that Thursday or even Saturday. I can do that, but I want to have you go over them first. That handout that I mentioned was the handout that I gave you on the extra practice problems on momentum with solutions. I'll show that to you tomorrow. If you're either in class or you're watching online, I'll make sure that some of you already know what I'm talking about, others don't, so I'll just make sure I clarify this. Okay, back to this question. What's the difference between one-dimensional and two-dimensional momentum problems? So, first of all, the difference is that one dimension is just that all along a single axis. So that means that all the objects are either headed north or south. There's no east combined with north or south. All the vectors are parallel. As opposed to 2D, you could have one object going north, another object going west. Okay, or you have even more difficult problems where you have one ball hitting another and then they split up and they move off at the two balls move off at, let's say this is ball one, this is ball two, this is ball one, this is ball two. The two balls head off at different angles. They don't move parallel or in line with each other. And that implies different math. The math here is different. Some of you are still not getting that. The math here is different than here. Here the math is straightforward. It's just adding and subtracting. Here the math is either, well, not usually, it always reduces to a right angle triangle. Okay, we can always find the components and then reduce the math to just using the Pythagorean theorem. Okay, then I gave you this problem. A cart traveling north 10 meters per second hits a cart traveling at 5 meters per second north. So they're traveling in the same direction. This is a one-dimensional problem. One-dimensional problem. Okay, I didn't give the masses here. That's not the point. You'll be given the masses as well, but I was going through this quickly, so I just said forget about the masses. Assume they're given. The first cart rebounds at 2 meters per second south. The main point of this is showing the math involved. It's all going to be adding or subtracting. There's no use of a Pythagorean theorem. There's no use of a right angle triangle here. And the math, therefore, is pretty simple. Just adding and subtracting. So what's the speed of the second cart? Sorry, I got to turn that off. Okay. So what's the speed of the second cart? So we plug in our values for the speed. Notice they're both going north. So one is at 10 meters per second. The other one is at 5 meters per second. This should be 5 here. Not 2. It should be 5. Rebounds at 2. Okay, so let's go through this. So the first cart's moving north at 10 meters per second. The second cart's moving north at 5 meters per second. So they're both positive values to begin with. Then they hit. The first cart rebounds at 2 meters per second. Rebounding means it heads in the opposite direction. It heads in a southerly direction, therefore we have to include a negative. And then you'll have to solve for the V2. It's just simple adding and subtracting. The M1, M2 are numbers, so they'll multiply with the 10, 5, and negative 2 to give you just other numbers. It's simple subtracting and adding. There's no squaring of terms. That's because it's a one-dimensional problem. As opposed to two-dimensional problems where you're going to make use of the Pythagorean theorem, right? You're going to find your px, you're going to square it, you're going to find your py, you're going to square it, and that's going to be equal to your, usually it's a p prime squared. These will all be primed. Okay? I'm just mentioning here, some people asked how many of these problems. I know there's at least one two-dimensional problem in the multiple choice, just at least one one-dimensional problem. And there's another two-dimensional problem in the written. So I'll have you spend time on that handout I was referring to. Again, for those who are unclear what that is, I'll show that to you tomorrow when I've got it. I got it at the school. And then you'll be clear as to what you're to cover before I go over it. I'll either go over the problems on Thursday or I'll just reserve it for a separate evening like we're doing now. I started an equilibrium problem, so let's kind of go over that again. Let's just redraw that. Try that again. So an equilibrium problem is with the object. Usually it's hung from a ceiling. That's what I'm going to go over tonight. I'm going to go over equilibrium and torque problems. So it's hung from a ceiling. You're given the angle. Let's say it's 70 degrees there. You may be given, say it's attached. Okay, to wall, you're given this here. This angle is 30. You're not interested in this angle here. You're interested in the angle that it makes. You're interested in this angle here. Okay, so it's, let's just draw this out so it's more clear. It's 30 in here. You're interested in the angle within here. What's that angle? So it must be the complementary. It must be 60. Okay. And then according to the Z rule, you're interested in this angle. You're always at the tail of the vector. Remember the vector are force vectors. You're interested in drawing out the angle at the tail of these vectors. This would be, I'm just going to call them F1 and F2. It's easier. I don't run into as many problems. There's less subscripts. Okay, so this angle here is 70 degrees. Z rule, right? Rehash that if you don't know why that's the case. So what you're interested in is finding is, remember there's always going to be some sort of third weight here. I don't know, you'll be given, let's say, 50 kilograms. So the question is, what do I do next? Well, what you're after is balancing this. You're trying to find F1 and F2, or just one of them. It's just one of them. You'll still have to include both in your equations. Actually, I'll draw it out. What you're trying to find then is the components. You're trying to find F1, F1, x, y, F2, F2, x, y. Why are you doing that? Why are those components so important? Because it's a balancing act. We know that it's this, whatever this object is here, it's not moving. Okay, it's not moving, it's stationary, and therefore it fulfills a condition. Sum of the forces in the x is 0, and then similarly the sum of the forces in the y is just a fancy way of saying the forces balance. So what does it mean in terms of the components that I drew? It means that F1x must be equal to F2x in absolute value terms. Okay, just interested in the absolute value. It means in terms of y, F1y plus F2y is equal to, this here gives us, this here is usually what we call the FG. It's just equal to 50 times the mass times 9.8. Okay, so it's approximately, I'm just using I'm going through this quickly. My calculator's at the side here, so it's roughly 49 newtons. All right, 490 newtons. That's 490 actually. 490 newtons, roughly. Okay, so 490. So again, these equations simply mean that the forces balance each other. The forces acting to the left are balanced by the forces acting to the right. The forces acting up, make sure you look at clearly the direction these purple arrows are pointing. If they're pointing in the same way, then they add. If they're pointing in the opposite direction, then they're on the other side of the equation. Okay, notice I converted the 50 kilograms to the approximate newtons. We work with force, not mass. It's the force that's balanced. Okay, so next, what's the next step? I'm not going to go through the whole equation, but I'll set it up for you. So just write down your components. F1 cosine of 70 is equal to F2 cosine of 60. And now usually we rearrange. You can rearrange for either F1 or F2. Set that up. Okay. You always have two equations. So usually the x is usually the simpler one. And then on the left side, plug in your values for the y component. F1 sine 70. You have to zero in here. It should be F1 sine 70. And then the other one is F2 plus F2 sine. And that angle there is 60. Again, it's an approximation. Yeah, running through this quickly. So, okay, so you'll have those two equations. This is your number one, and this is your number two. You're going to substitute the right-hand side of number one, what I just circled, for F1. Okay, actually, I like the different color. So, for F1. Substitute it in there. So you'll end up with, see, this could take too much time, but this is it. The rest is just math. I'll write it out for you. Don't forget to multiply by what comes after the F1. You can do this now. It's all math. You just have to factor this out now. Factor that out of each term. So I'll let you figure out the rest. That's a setup for solving it. Okay, let's do a torque problem. Remember, no matter if there's any problem that looks like this, right? just set up the equations. The equations will always have one unknown. And if you fiddle around with it, you'll be able to find out what that unknown is. But you'll need two equations. You'll need this, something that looks like this, something that looks like this. There'll be a little bit of variation depending on the problems. Now, do you always need two equations? No, you could. In general, it's a general step that you take. Just look at some of the other problems here. Yeah, okay, let's go straight on to a torque problem. I would go over, I'm giving you the basics that you're going to need. You're going to put these problems on your flashcards. You're going to study them first, and then you're going to turn to some of the other handouts that you have, homework that you've done, study that as well. Okay, I do have more handouts that I'll give you as far as practice, but you'll go over these reviews first. And I made a list. If you go back to what I just posted prior to announcing this meeting, I posted the days, the actual days where you have reviews. So go back to that. Those are the days you want to use in order to make up your flashcards, right? Including tonight, including tomorrow. You should be caught up. You should be caught up by tomorrow evening. We'll probably do one more lesson on Thursday. So just keep adding to it. You'll have all the way up to Friday night, even if you get it in by Saturday morning. I won't check, till about then. So you got enough time to get all of them down. If you want to add to the flashcards your own problems, you certainly can, but the bare minimum is have the problems that I've gone over in these reviews, right? Question and answer. Question on one side, solution on the other. And yes, if you want to stop it at this point here, you don't have to go any further than that. I think just for the sake of saving a little time, I think you probably could do the math from there. If you're confident you can do the math, I think I'm more than willing to. Like in this problem, it's a little long. You can just cut it short. That's fine. And now let's go on to a torque problem. So notice right away I said torque problem, and I drew a beam. What's missing here? Between this problem and what I just drew, what's the missing object? There's no beam here. So I started, because there was no beam, I didn't even say and mention anything about torque. Started with forces. The moment you see a beam, start with torque. Some of you are still forgetting that. Start with torque. And torque is not cosine. Torque, I don't give a crap what other people say. Use the sign. You can put the sign anywhere you want, but the sign is always there. It is not a cosine. I see that too many times. Don't use the cosine. As long as you set it up properly, it's not the cosine. Okay, having said that, some people will solve it with using the cosine. That's their prerogative, not yours. You're not going to do that. Not the proper way. So here's a little trick. This might throw you off. See, what's the angle that I need? Do I need this angle or this angle? Let's say I drew. Which angle do I need? Let's say I was given this angle. That's a possibility. Is that sufficient? You would actually use a cosine in that case, but I don't want you doing that. It gets confusing. Which angle? You want this angle here. You want to find it's a complementary in this case. Oops. It's done. Smaller. Okay, so it's a complementary. So it must add up to 90 degrees. So what's that? 5, 80, so 15. And it's 15 degrees. 15 plus 75 adds up to 90. That's the angle you're going to use when calculating the torque. So let's say you're given the length of the beam. So the L, remember, you don't have to always have the length of the beam. Sometimes you can cancel it out. As long as you have any of the lengths that you need in terms of some multiple of L, you can cancel L out. In this case, I'm going to give you the length. Let's say it's 5 meters. And making it up, it could be whatever. And let's say, you know what, I'm going to extend this. Extend it. Maybe a little farther out. Okay, so let's say this length here is 4 meters. Okay. Let's say we don't know what this force is. It's attached to the wall, so the wall's here. Okay, and there's like a hinge here, like a pivot. That's my pivot. Usually I draw with a triangle. Let's just draw with that semicircle there. So it could pivot there. And the mass of the beam is 100 kilograms. How would you set this up? Is there anything else or no? That's it. How would you find the force? First of all, how would you find this force? And then I'm assuming the force on the wall is upwards. It could be downwards, like that. But let's say we can assume whichever direction we want. It's either this way. Okay, could be in. No, that could be. Right? We can assume any direction we want. I'm going to assume this direction. If we assume the wrong direction, our components are going to be negative as opposed to positive. So it works out. The angle here, we don't know. Everyone makes that mistake. We don't know what that angle is. Now, it does have components. Okay, we don't know what those components are, but it does have components. We'll come back to that. We'll call that FW. How are you going to find F? That's the first question. Find the force on the string that's holding up this beam. Are you going to use this? To find F? Yeah? No? No, not till, you will use it later to find FW, but not to find F. The first step with a beam is to use this. So calculate the torques. Go over here, erase that, I don't need all that. So what's the torque here? I'll just call it tau. Tau is F times the sine, not the cosine, times the total length that the tail is from the pivot, measured along the beam, 4 meters. Okay, that's your first torque. Your second torque, looks like there's only 2 in this case, is due to the weight of the beam, Fg, which is 100 times 9.8. 9.81, but I don't know. Don't have enough room, so that's 980. Okay. What's the torque? That's what we're going to calculate. We don't simply need the force. We need to go further, calculate the torque. It's a beam. You need a torque expression. I'll call it torque G. 980, the force, times the sine of 90. It is a 90-degree angle. It's 1. We know it reduces. Times the length. What's the length? Is it 5? Use the full 5. No, it's at the midway point, so it's 2.5. It's 1/2 L. Half the length, half the 5 meters. Is it half the 4? No, we want to use the full length of the beam. The weight's considered to act dead center. So that 980 times 2.5 it reduces to. It's about 2,500. So those are the only two torques. There's no other forces that are. There's a force here, but that's not a force that's a distance away from the pivot. It's at the pivot. So the torque due to that is 0. Torque due to FW, torque, I'll call it tau W, 0. We don't need to count it. So all we have to do is, what does this say? It says something similar to this. It says the torques balance. Well, if there's two torques, all you have to write down is tau is equal to tau G. They balance. That's it. Well, I mean, you have to write out the expressions, but that's the main physics behind it. So it's F. You write this one down. Is equal to tau G, which is 980. I mean, you could plug it all in, calculate F. That's done. What about FW? Think about that. I'll give you 30 seconds just to think about it. How would you calculate it? Okay, now you're dealing with force. You go from this expression here to this expression, we talked about earlier. Okay, now you balance. This is, again, just essentially saying the forces must balance. Now you balance the forces. What are the forces? Well, let's look at this. Let's draw this out. Draw it out. This F has a component up. That's Fy. It also has a component and it should connect more clearly than that, but that's okay. That's Fx. You find your Fx and Fy. This is F. I have to zoom in here. This is F. W X. This is F W Y. So balance. What's the FX? What FX is bound? Which forces are parallel to the x-axis? FWX and FX. So you have FWX is equal to FX. That's the first thing. Okay, these two forces balance. That is equal to that. What else balance? Any forces pointed in the same direction are on the same side of the equation. So FWY plus FY, and anything whose arrow's in the opposite direction, this one here, the purple one, that's on the other side of the equation, FG. So if the arrow points in the opposite direction, that term that it represents is on the other side, in this case, the right side. That's it. And then, that's the physics. The rest is math. So what is FWX? FWX is FW cosine of an unknown angle. You don't know what it is. What's FX? FX is F times, you do know that angle. I think it's 15, right? Yeah, it's 15. 15. Okay? And then what about Fy? The Fwy is Fw sine of theta, which you don't know, plus F sine of 15. and that's equal to FG. Okay. So you know this, you know that, obviously. You don't know what the cosine of the angle is, right? I'm just trying to think here. Could you? Give me a minute here. Set this up properly. You do know this. You obviously know that. You know that. You don't know what FW is. I would just, you know what? Don't even worry about here. Let's go backtrack here. We don't even have to get that complicated. You can just write. Find the components. So just write F. Find the angles later. Find the components first. FW. You can do it that way like I did, but it gets a little complicated. So just keep it as F. FWX and FWY. And you can, now you got it. You can solve for FWX. What about FWY? Yes, you got everything else. You can solve for that. So you'll have your FWX and your FWY. You'll have it. And then you can solve for your FW. Going back here, your FW, once you got the X and Y components, use the Pythagorean theorem, and then use the tan of the angle to find the angle. So you have FW squared is equal to FWX squared plus FWY squared. And then for the angle, use the tan. Tan of theta is equal to FWY over FWX. Take a look at the triangle. See where I got the tan from. Tan is opposite. It's opposite over adjacent. That's the adjacent. That's it. Okay? So we've gone on for about a half hour here. I could extend it. I think that gives you a lot to cover. And we're going to go over a full class tomorrow. We will, let's see, I'll have 2 classes tomorrow. I'm going to do the morning and afternoon. So I'll have done the review probably by tomorrow afternoon. Okay, which gives us more time to go to zero in on the 2-dimensional problems. On Thursday, I can do them Thursday. Are there any questions you want me to go over now? Not too long of a tutorial, but at least it gives you something to work with, nibble on. Anyone got any questions? No? Just remember to transfer all of this, add this to your flashcards. The problem is, I heard, this is bloody a pain, but I've heard that with, you could put it in Notion, it's free in Notion, but if you were trying to do it in the other one, what's it called, Quizlet, you'd have to pay to load the pictures, to get the paid subscription. I don't want you doing that. So again, just buy simple flashcards. Transfer it manually. Physical, actually, it's probably the best, right? Because it's easy that you can carry it with you wherever you go. Just simply in a tablet or your notebook or your laptop, right? But I think physically, I know it sounds strange, but same thing to do with writing. Whenever you're studying and you do something more tactile, you tend to retain the information more. I don't know if you believe this or not, but when you're reading a book, they've done studies, a digital book compared to an actual book, and people who read from an actual book where they flip pages actually tend to retain the information better. So there is something to that tactile aspect. So writing it down, flipping through the cards with your hands, writing it down on the flashcards, that's actually best. So consider getting actual cheap flashcards. use that. Okay, so I'll see you guys tomorrow, regardless whether you're there or online, and we'll go over more and more. I think tomorrow I'll go over another torque problem and then start circular motion. And we'll have enough time to finish off, like I said, by tomorrow afternoon. It's not tomorrow afternoon, first class on Thursday. And then I'll do some more zero in on the momentum more on Thursday. And I'll do probably another class on another tutorial on Saturday or something like that. Okay, hope that helped. So I'll post this soon. You'll have, I did remember to record it, so haha. Take care. Have a good night.